In this video, we're going to be looking at complements and conditional probability. We'll start off with the at least one rule, which basically says that if you find the probability of a thing that you're not looking for, subtract it from 1, you'll find the probability of the thing that you are looking for. So in this case, it's specifically at least one of something. So for number 1, find the probability of tossing at least one head in 2 tosses of a fair coin. So I'm going to say probability at least one head. All right, so I'm following this model. Is going to be equal to 1 minus the probability of no heads. All right, so to apply this rule, all we would need to do is figure out the probability of not getting heads when you flip a coin twice, and then from there we just subtract it from 1. So the probability of not getting heads in 2 tosses, that's the same as saying getting tails and tails. All right, so we would be looking at this and saying probability of getting a tails multiplied by the probability of getting another tails. We can do the straight multiplication because they're independent events. Whether I get tails on the first flip of a coin will not impact whether I can get it on the second flip or the third or the 30th flip. It doesn't make a difference. Probability of getting tails is 1 out of 2. So 1 out of 2 by 1 out of 2 gives me a 1 out of 4. So that's telling me that if I were to flip a coin twice, then the probability of getting tails in both occurrences would be 1 out of 4. All right, but I don't want that. I want the probability of the complement of that. So I do 1 minus a quarter, which is 3/4. So what that's telling me, again, flipping a coin twice, there will be at least one head in 3 of the 4 possible outcomes. Another way of doing it, which works for a small number of trials, but as you increase the number of trials, it gets more complicated, would be to make a tree diagram. So first, flip. You could have either heads or tails. For the second flip, depending on what you got on the first, you can still get heads or tails. All right, so that's an independent situation. So you're not really depending on anything. Regardless of what you got in the first flip, you could still get heads or tails. So heads or tails, same deal here. You could also write this as a sample space. Heads, 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 tails, tails, heads, tails, tails. All right, so this is an alternative approach, but again, only really good for a small number of trials. Because if I flip a coin 30 times, imagine the size of that tree diagram. So I'm looking for an outcome that has at least one heads in it. Well, there's at least one here, at least one here, at least one here. 3 out of the 4 possible outcomes leads to getting at least one head. So 3 out of 4 would be the probability. All right. If I wanted to do that tree diagram approach for number 2, 3 tosses of a fair coin, I'd have to expand, 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 expand. I get heads, tails, heads, tails, heads, tails, heads, tails. This is right on the border of what I'd be willing to do. And then you could count up the number of instances in which there's at least one head, and you'd get 7 out of 8. So you could do it that way. It's not relevant to number 1, so I'm just going to wipe this out real quick. Instead, I'm going to use this rule. And you can see in number 3, that's where I kind of prove the point. 37 tosses of a fair coin. You know, you're definitely not going to want to do a tree diagram for that. All right. So again, no heads means all tails. So for this part here, I'd say the probability of getting tails times the probability of getting tails times the probability of getting tails. All right, and each one of those would be 1/2. But we want to kind of learn from this a little bit, because just thinking forward to the next problem, we're going to have to flip that coin 37 times. So we start thinking of shortcuts here. In this case, we had 1/2 times 1/2, which was because there were 2 instances of tails. That's the same as saying, oops, it's not the same as saying oops. It's the same as saying 1/2 to the second power. In this case, it's the same as saying 1/2 to the third power. So 1/2 to the third power happens to be 1/8. 1 minus 1/8 will give me 7/8. But now we just kind of gained something from this process, because in the next question, 37 tosses of a fair coin, I can just jump right to, instead of probability of tails times probability of tails times probability of tails 37 times, I could just do 1/2 to the 37th power. 1 minus that. Just go to my numworks here. Raised to the, this is the raised to the key, 37th power. Hit OK. It gives you a virtual approximation of it, because the ability for the calculator to handle numbers like that is suspect, right? But if you go to that one and actually hit OK on it or execute on it, it'll bring the decimal value. And you know, our normal strategy for rounding the 3 significant digits wouldn't really help here. So your choices are to write that whole fraction form, 13743895347 all over all that stuff except a 2 at the end. And or you can just say approximately equal to 1. Right? It's not really equal to 1. You got to be careful about that. If you were to say it's equal to 1, you're saying it's guaranteed to happen. I mean, it's virtually guaranteed to happen. If I flip a coin 37 times, I'm willing to, bet's a strong word, but I'd be very confident that it's going to involve a heads, an outcome of heads somewhere along the lines. If I were to flip a coin 37 times and all 37 of the outcomes were tails, I'd be questioning the fairness of the coin. We could also do it with dice. So here it's saying at least 1 4. So that's going to be 1 minus the probability of no 4s. All right, probability of getting a 4 when you roll a die, you know, a little diagram here to help out in case you're not familiar with a die or overly familiar with it. To get a 4 is one possible outcome out of one outcome out of 6 possible. So probability of getting a 4 is 1 out of 6. If I want no 4s, all right, so I can just kind of, and maybe I'll just sort of move this. Sort of, I'm actually going to move it. If I want not a 4, it's going to be everything else, the other 5 outcomes out of 6. We're rolling the die 6 times, so I would say 5 out of 6 raised to the 6th power would be the event that I rolled the die 6 times and every single one of the outcomes was something other than a 4. If I subtract that from 1, that'll get me the probability that at least one of those outcomes was a 4. All right, so putting it in my calculator, same deal. 1 minus 5 over 6. Close it up. Raise it to the, oh, sorry. I didn't close it up. I closed it up in the wrong spot. So let me get rid of that little closed paren. Hit the right arrow to get out of the denominator. Close paren, raise it up to the 6th power. Hit OK. A little bit more manageable on the fraction front here. So 31031 over 46656, approximately equal to 0.665. I'm inclined to just kind of just leave it that way.